Dear learners, I welcome you all to this module. The title of the module is Application of Linear System and Linear Independence. System of equations has many applications in real life. We are going to discuss some of its applications. The next important area we discuss here is the linear independence. From the linear independence of a set of elements, we will learn how to check the linear independence of matrix columns. We shall see some applications now. In this module, first we are discussing the interesting situations of real life where a linear system of equations can be used. It is usually expected that a real life problem involving linear algebra would have only one solution or perhaps no solution, but this is not the case. The main objective of this section is to show how linear systems with many solutions can arise naturally. Many applications can be seen in economics, chemistry and network flow. The three types of real life applications discussing here are linear system in economics, linear system with chemical equation, that too we will discuss in detail, and linear system with network flow. I will give you the material, you can read it. Remember, our goal is to convert all these types into matrix and then solve. A homogeneous system in economics we are going to see now. Suppose a country's economy is divided into many sectors such as various manufacturing, communication, entertainment and service industries. Suppose that for each of these sectors has a total output for 1 year and we know exactly how this amount is divided or exchanged among the other sectors in the economy. Let the total dollar value of a sector's output to be the price of that output. There must be an equilibrium price where each sector has income is equal to the expenses for all this trade. That is, Leontoff proved that there exist equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances its expenses. Here we can use the linear system to determine the equilibrium price of outputs for each sector. An example we shall see now. Suppose an economy consists of the metal, electric and steel sectors and the output of each sector is distributed among the various sectors. Like here a table 1 is given, you can see the entries later. The entries in the column represent the fractional parts of a sector's total output. The second column of that table for instance says that the total output of the electric sector is divided as follows, that is 40% to metal, 50% to steel and the remaining 10% to electric. Electric treats this 10% as an expense it incurs in order to operate its business. Since all output must be taken into account, the decimal fractions in each column must sum to 1. Denote the prices, that is dollar values, of the total annual outputs of the metal, electric and steel sectors by PM, PE and PS respectively. If possible, find equilibrium prices that make each sector's income match its expenditures. The table that we have spoken is on the screen now. We can see a sector looks down a column to see where its output goes and it looks across a row to see what it needs as inputs. For instance, the first row of table that is displayed says that metal receives and pays for 40% of the electric output and 60% of the steel output. Since the respective values of the total outputs are PE and PS, metal must spend 4 PE dollars for its share and of electric output and 0.6 PS for its share of steel's outputs. Thus, metal's total expenses are 0.4 PE plus 0.6 PS. To make metal's income PM equal to its expenses, we want PM to be equivalent to minus 4 PE plus minus 6 PS. The second row of the exchange table shows that the electric sector spends 0.6 PM for coal and 0.1 PE for electricity and 0.2 PS for steel. Hence, the income or expense requirement for electric is PE is equal to 0.6 PM plus 0.1 PE plus 0.2 PS. Finally, the third row of the exchange table leads to the final requirement, that is PS is equal to 0.4 pm plus 0.5 pe plus 0.2 ps. To solve the system of equations that we have listed 1, 2 and 3, move all the unknowns to the left sides of the equation and combine the like terms. For instance, on the left of the equation 2, write pe is equal to minus 1 pe as minus 9 pe. Therefore, we get the system of equation that is displayed on the screen now. Row reduction is our next step. For simplicity here, decimals are rounded to 2 places. You can see all the row reductions that is displayed on the screen now. The general solution is Pm is equal to 0.94 Ps and P is equal to 0.85 Ps and Ps is free variable. The equilibrium price vector for the economy has the form is given here on the screen. So, any non-negative choice for Ps results in a choice of equilibrium prices. For instance, if you take Ps to be 100 or $100 million, then Pm is equal to 94 and P is equal to 85. The incomes and expenditures of each sector will be equal if the output of metal is priced at $94 million and that of electric at $85 million and that of steel at $100 million. So, that is how we can apply the linear system in the field of economics. You can see in detail because we have skipped the calculation part, you can see that. Now, we are going to see how the linear system is useful to balance chemical equations. So, do we have to apply linear system in chemical field? Yes, of course we have to do that. So, now chemical equations describe the quantities of substances consumed and produced in a chemical reactions. So, you can take a look at the examples to see the process. Examples already there in the material. So, consider the chemical reaction where nitrogen and hydrogen reacts to form ammonia by an equation of the form X1N2 plus X2H2 that gives X3 and NH3. A chemist have to find whole numbers X1, X2, X3 such that the total numbers of nitrogen and hydrogen atoms on the left match the corresponding numbers of atoms on the right, because atoms are neither destroyed nor created in the reaction. To balance the equation, we have to find the numbers X1, X2 and X3. Now, we have to create the matrix. To balance the reaction, we have to construct a vector which lists the number of atoms of each reactant. The above equation involves two types of atoms, nitrogen and hydrogen. So, construct a vector in R square for each reactant and product that lists the number of atoms per molecule. That is as follows. You can see here we are creating a vector for N2, that is 2 0, for hydrogen this is 0 2, for ammonia NH3 it is 1 3. First entries in the columns denotes the number of atoms of nitrogen and the second entry denotes the number of atoms in hydrogen. To balance the chemical equation, the coefficient x1, x2 and x3 must satisfy the given equation, that is x1 multiplied by the column vector 2 0 plus x2 multiplied by 0 2 is equal to x3 multiplied by 1 3. So, in order to solve, move all the terms from the right to the left. Therefore, whatever you are getting, that is already listed on the screen, you can see, and after that we have to row reduce the augmented matrix, that is also here listed on the screen. You have to do the row reduction until we get the certain echelon form. That is, all the steps are on the screen, you can see. So, yeah, so this equation leads to the general solution of x1 to be equivalent to 1 by 2 x3 and x2 is equivalent to 3 by 2 x3, and here x3 is a free variable. So, since x3 is free, you can let x3 to take any value. I am going to take x3 to be equal to 2, since it is the smallest number which make all the coefficient to be a whole number. So, the equation also to be balanced if, for example, each coefficient were doubled. However, chemists prefer to use a balanced equation whose coefficients are the smallest possible whole numbers. Dear learners, now we have seen the application in two different fields, economics and chemistry. So, now we are going to see an application in network flow, but now we are not going to see that in detail. But interested learners can go through the material. In the material that is provided, the network flow is already included. Please have a look at the network flow if you are really interested. Now, we shall see the definition of linear independence. So, now we have a set of vectors, namely V1, V2 etc. Vp belonging to R power n, and this is said to be linearly independent if for the linear combination C1 V1 plus C2 V2 plus etc. Cp Vp is equal to 0 has only a trivial solution, that is all of the Cj should be equal to 0. So, that is what we mean by linear independence. I will repeat again. So, if you have a set of vectors, you have to say the set of vectors to be linearly independent to each other. Then for any linear combination that is equated to 0, the coefficients that we are talking about, that should be equal to 0. So, only then we can say the set of vectors is linearly independent. So, from here, what is the definition of linearly independent? For linearly dependent, you might have guessed, right. So, if you have a vectors and if for some linear combination that is equated to 0, if at least one of these variables, that is coefficient Cj's, are not equal to 0, then those kind of set of vectors are said to be linearly dependent. So, from here we can get the definition of linearly dependent also. For linearly dependence, you have to have at least one Cj should be non-zero element. So, now based upon this concept, we shall see some examples. So, we have now V1 as a vector 1, 2, 3 and V2 to be equal to 2, 5, 7, V3 is equal to 1, 3, 5. So, we have to check whether these three are linearly independent or not. So, consider C1 V1 plus C2 V2 plus C3 V3 is equal to 0. So, here C1 I have substituted the values of V1, values of V2 and values of V3, and this is 0 vector 0 0 0. So, I am getting this matrix, that is C1 plus 2 C2 plus C3 equal to 0 and 2 C1 plus 5 C2 plus 3 C3 here, 3 C1 plus 7 C2 plus 5 C3, here I have 0 vector, and what I am going to do is I am going to form an augmented matrix from here, that is I will have 1 2 1 and 0 here, right, and then 2 5 3 0 3 7 5 0. So, I have formed this matrix from the previous thing, and what I am going to do is I am going to go with the row operations. I am going to reduce this to an echelon form. So, therefore, I am doing some row operations here. The row operations is my choice. I can do my own operations as long as the logic holds. Therefore, I am getting in the final step, I am getting 1 0 0 0 0 1 0 0 0 0 1 0. From here, my values of x1 is 0 and x2 is 0 and x3 is 0. So, you can see the value of x1 is equal to 0, x2 is 0 and x3 is 0. Therefore, you can very well say that, so if this has to be equal to 0, then all of the values x1, x2, x3, or in fact you can have instead of this x1, x2, x3, here we have considered c1, c2, c3, right. So, this is c1, c2, c3, that is equal to 0, not x size. Therefore, which means that whenever this combination is equal to 0, the only solution that we are getting is all of the variables C1, C2, C3 should be equal to 0, which means that the set consisting of V1, V2, V3 is linearly independent. Now, we shall see about linear independence of matrix columns. Here we have considered A as a column vector, A1, A2, etc. An, where Ai represents the ith column, and we have V to be equal to V1, V2, etc. Vn. Now, AV is equal to 0, that is, if the columns of A should be linearly independent if and only if this particular thing AV is equal to 0 has a trivial solution as its only solution. Now, we have to aware of this fact also. The determinant is not 0, then the corresponding column vectors are independent. The determinant is equal to 0, then the corresponding column vectors are dependent. Please know that. So, now with respect to this, we shall see some examples. The first one, we have this matrix 1, 3, 5, 2, 4, 4, 1, 0, minus 1. And we told no, if the determinant is non-zero, then it is linearly independent. So, now for that I am just finding the determinant. I am getting the determinant to be minus 6. Minus 6 of course is not equal to 0. From here itself I can say the column vectors are linearly independent. This is one procedure. The other one is, from here we can prove, consider Ax equal to 0. From this step, form the matrix, corresponding augmented matrix. I am getting 1, 3, 5, 2, 4, 4, 1, 0, minus 1. and the last column I have 0 0 0 because that is what I am considering, x equal to 0, that is what the condition also says. Therefore, while solving, while reducing it, the row in its echelon form, I am having 1 0 0 0 1 0 0 1 0, here 0 0 0. So, from here the value of x1 will be equal to 0, x2 is equal to 0, x3 is equal to 0. So, which means that the only solution of x equal to 0 corresponds to x1 is equal to 0, x2 is equal to 0, x3 is equal to 0. That simply means column vector of this matrix is linearly independent. So, in this way also we can prove the column vector is linearly independent. Now, we shall talk about a set that contains 1 vectors or 2 vectors, that is a set of 1 vectors or 2 vectors. What happens if you have only one element in a set? So, the element that you are considering, if it is non-zero, definitely that is going to be a linearly independent, right. So, if you have a 0 vector, then that set is a linearly dependent set. Why is it so? Because if you have a 0 vector, let it be 0 containing, so consider this linear combination C multiplied by V1 or C1 V1 is equal to 0. Your number is already 0, your element is already 0, therefore C1 multiplied by 0 is equal to 0. So, therefore, in the place of C1 you can substitute any value, right, maybe 1, if C1 is equal to 1, you are going to still get 0, which means that no matter what the values of C1 all the C1 V1 will always be 0 because your vector V1 is 0. In this case, your only solution is not the trivial solution, you have so many solutions, right. Therefore, a set containing 0 vector or 1 0 vector, that is only 1 0 vector, will become linearly dependent, whereas a set containing only 1 non-zero vector is linearly independent. We are talking about set consisting of 1 vectors. So, what happens if you set contains 2 vectors? Let it be V1 and V2. V1 and V2, the set containing 2 vectors, becomes linearly independent if none of them is a multiple of one another. For example, if you have V1, V2 containing in one set, then V1 should not be a multiple of V2. So, if this is the case, then your set becomes linearly independent. If at least one of them is multiple of another, then your set becomes linearly dependent. It is very easy to verify this fact also based upon the linear combination, you can easily verify that. So, now we have talked about set containing 1 vector, we have talked about set containing 2 vectors, but in reality we are not restricting the number of elements in a set, right. Therefore, what happens when your set contains more than 1 vector? So, that is what we are going to prove or discuss in the next theorem. So, we are having a set consisting of n elements V1, V2, etc. Vn. So, this set becomes linearly dependent if and only if there exists a vector here in the set that can be written as a linear combination of the preceding vectors, which means that there should exist at least one vector which is the linear combination of the remaining vectors or the preceding vectors. So, if it is possible, then we can say the set we are considering is linearly dependent. If it is not possible, then the set is linearly independent. So, that is what we are going to prove now. As usual, this has necessary part and the sufficient part. So, first we will prove that we will take the set to be linearly dependent, and we shall try to prove there exists one vector that is a linear combination of the preceding vectors. So, for that I have assumed my set to be linearly dependent. So, if your set is linearly dependent, if you have V1, if you have only one element, V1 is equal to 0, and automatically that is a linearly dependent set. For example, if you have at least one element here that is equal to 0, maybe let it be V1 is equal to 0, then what happens, we can very well write the 0 as a linear combination of the other vectors. How can you write? You can write 0 multiplied by V2 plus 0 multiplied by V3, we can do like this, no. Therefore, if P1 is equal to 0, then there is no problem. Therefore, we are going to assume the set is not equal to V1 is not equal to 0, and C1, consider C1 V1 plus C2 V2 plus etc. Cp Vp is equal to 0. So, now listen. So, here we have assumed our set to be linearly dependent, and we have considered the linear combination, and we have equated that to 0. Since the vector is linearly dependent, there should exist at least one Cj such that the value of Cj is not equal to 0, that is a non-zero Cj, at least one. So, what we are going to do is, we are going to pick the least j such that Cj is not equal to 0, and we are telling that the j cannot be equal to 1. What happens if j is equal to 1? If j is equal to 1, then C1 V1 will become 0, right? Why is it so? Because C1 is 0, therefore C1 V1 is equal to 0. So, which means V1 is equal to 0, hence j cannot be equal to 1. Therefore, j should be greater than 1. So, I am taking C1 V1 plus C2 V2, in between I should have Cj Vj, and that is should be equal to 0. So, here from here I can find Cj Vj to be equivalent to minus C1 V1 minus C2 V2 etc. minus Cj minus 1 Vj minus 1, or otherwise you can say like you can choose j in such a way that Cj is equal to 0, non-zero, and the rest of the entries may be 0. That is one way of choosing Cj. Anyhow, you will have the linear combination of Cj Vj to be minus C1 V1 minus C2 V2 etc. minus Cj minus 1 Vj minus 1, the rest of the entries may be equal to 0. You can choose like that. Therefore, from here Vj is equal to minus C1 by Cj V1 minus C2 by Cj V2 plus etc. minus Cj minus 1 Cj divided by Cj Vj minus 1. Therefore, here Vj is already written as a linear combination of the preceding vectors. So, we have assumed the set to be linearly dependent. We are able to get Vj as a linear combination of the preceding vectors, and the existence of such j is also confirmed. Therefore, this proves the first part. Now, the next part, we are going to assume that exists one Vj, that is the linear combination of the preceding vectors. That is what we have assumed, that we have taken that vector to be Vj, and we have written as a linear combination. So, now if you bring all the terms to one side, and you will have 0 on the other side, right. So, which means that if you bring all the terms to one side, or if you bring this Vj to the next side, what is the coefficient of Vj? Coefficient of Vj when you bring to the next side is minus Vj, minus 1. Therefore, here you will be having minus Vj, therefore, the coefficient is minus 1. So, you can see here, this is one such linear combination, and the coefficient of Vj is minus 1, that is not equal to 0. That confirms the set is such that we are considering is linearly dependent. Therefore, we are able to prove whenever a set consisting of one or two or more elements, that is linearly dependent, if and only if there exists a vector that can be written as a linear combination of the preceding vectors. And while proving, you have to be very careful the choice that you are making for j. If you make the correct choice and arrange the terms in such a way that you will be having Vj as a linear combination of the preceding vectors. That is our one extra step here. We shall see two more theorems. The first theorem states, let S is equal to the set containing from V1 to Vp be a set of vector in R power n. If P is greater than n, then the set is linearly independent, and the proof is quite simple. It is already given in the material. Please go through the proof. And the next theorem states that let S is equal to the set containing from V1 to Vp. This is a set of n vectors, P vectors in R power n, and if the set S contains the 0 vector, then the set S is linearly dependent. This proof is also left to the learners. You can see the proof in the material. So, now we are at the end of this module. In this module, we discuss some problems of application of linear system in economics, chemistry, and the network flow is given for you to read. And the next important area we discuss here is the linear independence. From the linear independence of a set of elements, we learned how to check the linear independence of matrix columns. I hope this module will be of great use to you. We will see in the next module. Thank you.